So far we have been talking about signals with a finite energy content and signals which are absolutely integrable over the infinite range of time from minus infinity to plus infinity. You might recall that I mentioned earlier that we can extend the concept of the Fourier transform to signals which are not absolutely integrable over the infinite range, and in particular I mentioned that signals like u of t, a DC term, sin omega c t, cos omega c t, such functions also admit Fourier transforms provided we use impulse functions which are justified from the theory of distributions in mathematics. We would now like to familiarize ourselves with some of the operational rules involving such functions. We will not go into the deep mathematical details of this. We will just assume some results and use them to derive the Fourier transforms of signals whose energy content is not necessarily infinite or which is not finite. So, to start with, we would like to have some useful relations. We have discussed earlier this function sin theta by theta. This will have a variation like this with an amplitude 1, and this will be pi, this is minus pi. Sin theta versus theta. We are interested in the value of the integral of such a quantity. Suppose we say 0 to theta of say sin alpha by alpha d alpha. Such an integral is referred to as sine integral of theta. This is given the symbol SI of theta. Sine integral of theta is sin alpha by alpha from 0 to theta, and the variation of this is pronounced as sine integral of theta versus theta would be something like this. Asymptotically, it reaches a value which is equal to pi by 2. So, this is a relationship which we will assume. That means, if you start from this point and go on integrating, it reaches a value pi by 2. That means, the integral, the area under this curve starting from theta equals to 0, theta to theta equals infinity will be pi by 2, which it is easy to remember this particular value, because if you take this triangle, this is pi, this is 1, the area of the triangle is pi by 2. So, the area of this triangle is pi by 2, and that is also the area under the curve from 0 to infinity, which means that the rest of the area, this one and all add up to 0. The positive areas are cancelled out by the negative areas, and therefore, the area under the curve of sin theta by theta from 0 to infinity equals pi by 2. So, we have the relation therefore, 0 to infinity of sin theta by theta d theta equals pi upon 2. Now, sometimes we would like to have, instead of theta, we have sin a theta by theta d theta 0 to infinity. Now, if a is positive, then certainly you can say d of a theta by a theta, then this is the same relation as this, and the limits are not interchanged. Therefore, this will also be equal to pi by 2, because a theta can be replaced by another variable x. But if a is negative, then no doubt d a theta by a theta, a can be cancelled out, But if a is negative, instead of plus infinity you have minus infinity, and you know sin theta by theta is a even function of time, but you are integrating in the negative direction, therefore it will be minus pi by 2. So, the result is this value is pi by 2 for a greater than 0 equals minus pi by 2 for n. Or in other words, if you extend the sin theta, sin integral theta in the negative direction, it will be like this, and it reaches minus pi by 2 eventually. This is a relationship which is useful for us in our work. Just to illustrate this particular rule, let us consider an example once again. Find inverse Fourier transform of AD sin omega d upon by omega d upon 2. We know the result. We know that sin omega d upon 2 by omega d upon 2 times AD is the Fourier transform of a pulse function of amplitude A and width d centered around the origin. But we would like to find this out independently. So, let us do this. So, f of t would be 1 over 2 pi, and I take out this d by 2 outside, therefore, it will be 2a by t, 2a by 2a, integral from minus infinity to plus infinity of f of j omega, which is sin omega d upon 2 divided by omega d e to the power of j omega t d omega. That is the inverse Fourier transform of this function. This I can write as a upon pi minus infinity to plus infinity sin omega d upon 2 cos omega t dt d omega plus minus infinity to plus infinity sin omega d by 2 sin omega t d omega and a j sin in front. J sin in front. Now, this also by omega will continue to have here. What you observe here is, as far as the second integral is concerned, sin omega d upon t divided by omega, this is an even function of omega, this is an odd function of omega, and you are integrating between symmetrical limits from minus infinity to plus infinity. So, the contribution of this integral from minus infinity to 0 would be exactly equal and opposite to the contribution that arises from 0 to infinity. So, since this entire function is an odd function of omega and you are integrating between symmetrical limits, this goes to 0. So, what we have left with is only this, and this can be written further as you have sin theta and cos theta, therefore, you can combine these two as sin alpha plus beta plus sin alpha minus beta type of formulation you can make. Therefore, I can write this as a by pi, and then you have 2 also will come in, because you are going to express this as sin alpha plus beta and sin alpha minus beta. So, you have sin of omega t plus d by 2 divided by omega, that is d omega, and minus infinity to plus infinity of sin omega d by 2 minus t by omega d1. So, you have two such terms. Okay. Now, we can also observe here first of all before doing this, before going further, that this is an even function of omega, this is an even function of omega. Therefore, whatever integral you get from minus infinity to plus infinity would be twice the value of the integral which we would have got if you extended, if you integrated this from 0 to infinity. So, I can write this further as 4a upon pi, then 0 to infinity and 0 to infinity here also, that also I can write this here. So, I will do that. Let me see. Yeah. Okay. Now, I think this should be corrected. First of all, since I am doing the integration from 0 to infinity, I should have 2a upon pi, but sin omega t d by 2 sin omega d by 2 minus t will give me 2 times sin omega d upon 2 to cos omega t. Therefore, I must divide by 2 further. Therefore, this will finally this will become a upon pi. So, a upon pi, this integral from sin omega t plus d upon 2 by omega and sin omega d by 2 minus d omega. Suppose I call this integral I1 and this integral I2. And let us see what their values would be for different values of t. For this, I make use of this relation here. Sin a theta by theta d theta will be pi by 2 for a positive and minus pi by 2 for a negative. Therefore, if I plot I1, the value of I1, we have sin omega something by omega d omega, something very similar to this, and instead of a I have t plus d upon 2. So, as long as t plus d upon 2 is positive, it is pi by 2. As long as t plus d by 2 is negative, it is minus pi by 2. That means, this value of this integral will be like this. This is pi by 2, this is minus d, this is t, and this is minus pi by 2. So, as far as I1 is concerned, it will have a positive value of pi by 2 for t greater than minus d. So, that t plus d by 2 is greater than 0, and as long as t plus d by 2 is negative, it has minus pi by 2. That is the value of I1. Value of I2, again the same formulation should be used. We have sin omega by omega d omega, but omega is multiplied by d by 2 minus t. Look at this expression again. Sin a theta by theta d theta is pi by 2 for a positive, minus pi by 2 for a negative. So, as long as d by 2 minus t is positive, then it is pi by 2, otherwise it is negative. That means, as long as t does not exceed d by 2, then it is going to be pi by 2, otherwise it is minus pi by 2. So, as far as this will be the relation that you get finally as far as I2 is concerned. So, what do we have got for when you add I1 plus I2? Now, we no longer need this. So, if you add I1 and I2, add up these two things, then this positive area will be cancelled by the negative area here and here. So, you will be left with a pulse like quantity which will have a value of pi by 2 and pi by 2, this is pi by 2, this is minus pi by 2, therefore, this is pi, and this lasts from minus d to by 2 to plus d by 2. Yeah, I should have put here, because I have got t plus d by 2 and t minus d by 2, I should have written here minus d upon 2 and this also plus d upon 2, right. Therefore, this pulse extends from minus d by 2 to plus d upon 2, and therefore, this is the value of I 1 by I 2. Therefore, you multiply by a by pi. So, f of t would be a pulse of width a lasting from minus d by 2 to plus d by 2, a result which we would have expected from this. So, what we have really done is, we know in the forward direction, if this is the pulse, this is the Fourier transform. We demonstrated its validity in the reverse direction, making use of the relation of this sine integral as the argument goes to infinity. Illustrated this because we might like to use this type of formulation later on in our further work.